Hello students. In this video lecture, I have discussed the concept of electric potential difference and discussed a few examples based on electric potential difference and electric potential. By definition, electric potential difference between 2 points is defined as the work done in moving a unit positive point charge from one point to the other. Here, the work done is work done by external agent against electrical forces in moving the charged particle without acceleration. Electric potential difference between 2 points is represented by VAB. WAB is the symbol used for work done by external agent against electric field in moving a charge Q from point A to point B. So by definition, electric potential difference between points A and B is VAB equal to WAB divided by Q. But we already know that work done by external agent is negative of work done by electrical forces, and so given by the integral A to B minus Q into E vector dot dl. Putting the expression for work done in the expression for electric potential difference, we get VAB equals to minus integral A to B E vector dot dl vector. Thus, electric potential difference between points A and B is the negative of line integral of electric field between point A and point B. A little mathematical application and the application of concept of electric potential will help you prove that electric potential difference between points A and B is equal to the difference between electric potentials at point B and point A. I leave that as an assignment for you. Now since VAB is equal to WAB by Q, and since VAB can be written as VB minus VA, so WAB, work done by external agent, is given by the formula Q multiplied by VB minus VA. That is an important result and should always be remembered while working out a few basic questions on the concept of electric potential. Our next discussion will be on finding out electric potential due to a uniformly charged ring at a point on its axis. Here we will calculate the electrostatic potential due to a ring charge of radius r at an axial point P. We are assuming that the ring is uniformly charged, although you will see that you will get the same result even if the ring is non-uniformly charged. For finding out electrostatic potential at point P, we will use superposition principle. That means we will add up electric potential at point P due to all the small elements of the ring. We have taken a small element dq of the ring at the highest point, as you can see. The distance r, smaller, of point P from this element is equal to square root of capital R square plus x square. Electric potential at point P due to element dq is given by dV equal to 1 by 4 pi epsilon 0 multiplied by dq by r, where for r we have written under root r square plus x square as the value. Using superposition principle, the net electric potential at point P is the integral of the elemental electrostatic potential at point P due to element dq. So the final expression for electric potential at point P due to the ring is V equal to 1 by 4 pi epsilon 0 multiplied by capital Q by under root r square plus x square, where capital Q is the total charge carried by the ring. Let us start with a few basic problems on electrostatic potential and electrostatic potential difference. 12 joule of work has to be done against an electric field to carry a charge of 0.01 coulomb from point A to point B. find potential difference between points A and point B. Here we shall directly use the expression for work done by external agent in bringing a charge Q from point A to point B. By definition, work done by external agent is equal to charge Q multiplied by VB minus VA, which is nothing but electrostatic potential difference between points A and B. So that gives VB minus VA is equal to W by Q. Since W is equal to 12 joule and Q equal to 0.01 coulomb, so the result is 1200 volt. Now because we have to find out VA minus VB, so it will simply be equal to minus 1200 volt, and that is the final answer to this question. In this example, we are finding out electric potential due to a uniformly charged disk. Let us assume that the surface charge density of the disk is sigma coulomb per meter square. In order to find out electric potential at point P due to this distribution, we consider an elemental ring of radius y and thickness dy as shown in the figure. Because it is a surface distribution, so the elemental charge on the ring will be given by dq equal to sigma multiplied by 2 pi y multiplied by dy. Now we will use the expression for electrostatic potential due to a uniformly charged ring to find out electrostatic potential dV at point P due to the elemental ring. This potential dV is equal to k dq by under root x square plus y square, where k stands for 1 by 4 pi epsilon 0. Substituting the value of dq, we get dV equals to k multiplied by sigma multiplied by 2 pi y dy divided by under root x square plus y square. Now to find out electric potential at point P due to the disk, we integrate the elemental electrostatic potential due to the ring over the entire disk. So we get V equal to integral dV equal to integral of 2 pi sigma multiplied by k multiplied by y dy divided by under root x square plus y square. Here we have simply integrated the expression for elemental electric potential due to the ring. On integrating, we get V equal to sigma by 2 epsilon 0 multiplied by under root x square plus y square. The limit is 0 to r. On substituting the limit, we get V equal to sigma by 2 epsilon 0 multiplied by under root x square plus r square minus x, and that is the final solution to this question. Our next problem is on finding out electrostatic potential difference between the centers C1 and C2 of two charged rings carrying charges Q and minus Q distributed uniformly throughout their length. To solve this question, we will find out electric potential at centers C1 and C2 due to both the rings and find the difference between them. As we know, electric potential at point C1 is equal to sum of electric potential due to the first and the second ring. Similarly, at C2 the total potential is equal to the sum of electrostatic potential due to the rings with positive and negative charge. Let us proceed with the solution. Now at the center of the first ring, that means at point C1, the electrostatic potential is given by kq by r minus kq by under root a square plus r square. Here the first term is the electrostatic potential at point C1 due to positively charged ring, and the second term is electrostatic potential at C1 due to negatively charged ring. Similarly, at point C2, the electrostatic potential Vc2 is given by minus kq by r plus kq by under root a square plus r square. The first term again represents the electrostatic potential at C2 due to negatively charged ring, and the second term is the electrostatic potential at point C2 due to the positively charged ring. When we find out the difference, we get Vc1 minus Vc2 equal to 2kq multiplied by 1 by r minus 1 by under root a square plus r square, and that is the final answer to this question. In this question, we have a uniformly charged ring of radius r carrying a charge q. At a faraway point along the axis of a ring, a charged particle having a charge plus q and mass m is located and is projected towards the center of the ring. We have to find out the minimum speed of projection so that the particle may cross point C. To cross point C, the velocity at point C should be greater than or equal to 0. Now, since the charged particle initially is located at a faraway point, so there is no interaction between the charged particle and the ring. So electrostatic potential energy of the charged particle will be 0. Now, as the charged particle reaches the center of the ring, the potential energy of charge q at point C is equal to q multiplied by electric potential at point C due to the ring, equal to q into Vc, where Vc is the electrostatic potential at the center of the ring due to the ring. This reduces down to 1 by 4 pi epsilon 0 into capital Q multiplied by small q divided by capital R. Kinetic energy at point C is given by half m into Vc square. Now let us apply energy conservation and condition for charged particle to cross point C. We get half m into Vc square is greater than or equal to 1 by 4 pi epsilon 0 capital Q into small q by r. This is because the velocity at point C should be equal to or greater than 0 so that it may cross point C. So from this equation we get the value of Vc as under root 1 by 4 pi epsilon 0 capital Q into small q by m into r, and that is the final solution to this question.